Yeah, I am Will Noble, and I used to work at Google, but now I'm basically just some guy who put in 7 years at GCP working on various things and quit last summer to focus on what really matters in life, which is, of course, playing around with esoterica in the cloud. So yeah, basically for many years, I've had this fascination with WebAssembly now, and there are really so many different angles you can look at it from that I'm honestly in danger of just completely digressing at any moment here, but basically, I'm here to argue my thesis about what makes it such a powerful technology for the cloud. And it largely boils down to its additive approach to isolation and the richness of the interface it provides. Now, that sounds painfully abstract, but when we follow all the implications of that, we can find some drastic improvements to the economics and ergonomics of many cloud workloads. So you guys probably heard of WebAssembly, and anybody who's remotely connected to the WebAssembly community in the past 5 years has probably seen this tweet. So this is Solomon Hykes, co-founder of Docker, saying, if WebAssembly and WASI existed in 2008, we wouldn't have needed to create Docker. And it's pretty easy to see why this went viral. I mean, the guy who co-invented this foundational computing technology apparently disavows his own invention. So, by the way, he's talking about the WebAssembly system interface there, which is sort of like the standard library for WebAssembly. It does things like file system and socket APIs and other stuff. But, on the surface, WebAssembly and WASI together are going to provide a lot of similar capabilities and security properties as are available to Docker containers. So a lot of people basically interpret this tweet to mean that it's this drop-in replacement. And honestly, it kind of reads that way to me. But of course, viral tweets tend not to be the most nuanced. And a couple months ago, Solomon posted this interview on his LinkedIn where he revisits the subject and says, among other things, if you're talking about replacing containers, you have to talk about replacing Linux. Now let me get one thing straight. I love Linux. Plus, containers have this undeniable advantage of supporting your existing hot mess with its million dependencies as it is. They're super general in that way. And for many people, that's the most important feature. But WebAssembly can be a more natural fit for a lot of untrusted code use cases. And if you know much about server-side WebAssembly these days, you might know about how much energy has been going into these serverless WebAssembly platforms recently. Things like Cloudflare Workers and Fermyon Spin and Wasm Cloud. There are a lot of places where WebAssembly shows promise, but I'm going to try to keep this as concise as I can and focus on that particular use case, these serverless microservices. All right. First, let's back up. What is WebAssembly? How is it like Docker? How is it different? How is it like other virtual machines that came before it, like the JVM? Well, as the adage goes, WebAssembly is a lot of things, but it's not really assembly, and it's not really about the web. It is a sandbox virtual machine and a compiler backend target. It is supported in every major web browser where it is used to run untrusted web code with near native performance, but that also makes it a nice fit for plugin systems or the cloud or running LLM generated code or where platforms also have to run these diverse untrusted pieces of code safely. It provides strong isolation and memory safety guarantees that make things like stack smashing impossible, among other things. And really, it just approaches the whole isolation problem from the opposite direction from where Docker approaches it in containers and virtual machines. Because whereas processes within a container operate under this presumption of privilege, in a big virtual Linux world that has to be constrained by the runtime, WebAssembly modules can't do anything by default. They're inert. So only by importing and exporting these high-level functions to and from a host can a module actually do anything of consequence, like I/O. And this additive approach to isolation simplifies attack surface analysis, but it also makes isolation for WebAssembly a lot cheaper than it is for containers or VMs, and I'm going to show examples of that later. Now, I know I just downplayed the web and WebAssembly, but browser buy-in is pretty important. I mean, people in this room are probably getting deja vu for Java applets right now because the JVM is a virtual machine too, and it used to run in browsers. Of course, applets are deprecated now in every browser because they had a bunch of security and practicality issues. You know, there's also just a lot of Java baggage that comes with targeting the JVM, things like, you know, class-based object orientation, garbage collection, lots of pointer chasing, these things that you have to do when you work with the JVM. And WebAssembly takes a bit of a different tack. It has this sort of lowest common denominator approach that means it can really better support pretty much any language paradigm, as well as hardware features like SIMD. So right now, it has good support for Rust, Go, any LLVM language like C++, and rapidly evolving support for languages like Python, Ruby, JavaScript, and even JVM languages too. And that breadth of support is thanks in no small part to this massive incentive for language developers to support running in the browser. Now, WebAssembly also has this thing called the component model, which includes a richly typed high-level interface system called WIT. So this allows modules written in any of these languages to interact with modules written in any other language in a safe, natural way, sharing first-class functions and data types, and even between languages that manage memory in profoundly different ways. The component model is also a lot of things. I think maybe most important, it's sort of the closest thing we have to like a real universal ecosystem of software libraries, but that's a whole digression right there. So anyway, let's get back to our cloud use case. What is a serverless microservice besides just an annoying mouthful? Well, we can start pretty easy here. They're small. It says it right there on the tin. They gotta be smaller than the macro services or else this buzzword wouldn't make any sense. And that implies overhead. We might say that the boilerplate to business logic ratio is gonna be higher in one of these microservices. And that's because each container generally has to bring its own HTTP stack at a minimum, and other infrastructure like message encoders and decoders, telemetry, auth, quota, a bunch of stuff. Now for a microservice, this can easily add up to the vast majority of your image size. See, here's where the generality of containers actually works against us. Because containers can only afford a very poor interface to the outside world without sacrificing some of their sweet generality. Think about typical containers are going to expose a TCP port and maybe mount a volume, and that's pretty much it for the interface as far as the platform is concerned. And that's actually just too general for a platform to handle many features on behalf of all containers. So that boilerplate has to be injected into each container individually, multiplying the boilerplate by the number of containers. I'll give some examples later, but this seems like a sort of fundamental trade-off. On the other hand, WebAssembly components can have a very rich interface thanks to the component model, which provides the platform with basically just this greater understanding of the capabilities and needs of each component. See, this richer interface has several implications. Importantly, it can be leveraged to consolidate basically all that boilerplate into the platform, where a single copy can be shared among every workload. And thanks to WebAssembly's more finely controlled virtual machine, even things like a thread pool can be shared between workloads, providing, completely transparent green threading to applications, basically as efficiently as possible. But this all boils down to a lot of efficiency gains and cost reduction. So they also scale up and down automatically. This is pretty huge. It totally abstracts away the capacity problem, and it enables serverless's killer pricing feature, which is that you're billed for exactly how much you actually use the platform. It also creates this cold start latency problem, and it tends to be the most profound factor affecting the design of these platforms, particularly the scaling down part, because basically your container can shut down pretty much whenever. And in practice, This tends to require almost complete separation between compute and state. An external database is pretty much required. See, any process that runs longer than like a single normal RPC has to worry about checkpointing and synchronizing with other nodes, picking up slack when other nodes go down, and just generally solving some annoying distributed systems problems that can really detract from the simplicity of the serverless paradigm. But what if WebAssembly could actually eliminate the ephemerality problem, obviating the need for a database at all in certain long-running serverless use cases? See, with containers, it's considered intractable to try to pause a running process and move it to a different machine where it could be resumed as if nothing had ever happened in the first place. But with the WebAssembly virtual machine, it actually provides this layer of abstraction that makes doing this much more practical, at least in theory. I don't think there's any WebAssembly runtimes you can do this with today, but I've had some very encouraging conversations with some maintainers about it. They also tend to have a high degree of interconnectedness. So this comes with some advantages and a decent amount of baggage. For one thing, it's going to let you scale finer-grained components independently of one another, which can deliver some meaningful efficiency gains at scale. But it also complicates things like observability, deployment, regionalization, version interoperability, etc. See, serving a modern microservice mesh is going to require adhering to a bunch of best practices. And that's not exactly a big hurdle for a capable team. But another consequence of the richness and visibility afforded by the component model as an interface is that it can enable more advanced features to sort of be built into the platform and supplied in an intelligent way. And it can eliminate some of the operational overhead associated with microservices. So what does this richer interface actually look like? How can we actually get one of these components to run in the cloud? Well, WASI comes with this nice HTTP API. This is sort of what it looks like at a high level, expressed in that WIT language I was talking about. And basically, any component that wants to serve HTTP requests can just export that handle function there from the top interface. And if it wants to send outgoing requests, it can just import that bottom function. And this already gets us most of the way there. I mean, this already allows the platform to handle a lot of stuff for us, like the whole wire protocol, the whole connection juggling, parsing basic things like request method and path and headers into this rich incoming request structure. It still can't handle some other things we might want, like path-based routing or JSON serialization, right? So basically, that boilerplate would still need to be duplicated into each component. And do we really need 100 redundant JSON parsers just to run 100 microservices? I don't know. I think we can do better than that. Now, if you guys have ever used Kubernetes or wandered within earshot of a Google campus, then you've probably heard of gRPC. gRPC also comes with a rich interface definition language based on protobuf. And the terminology can get a bit confusing because actually that IDL is actually a lot more general than just gRPC or protobuf, but I'm going to call it gRPC. And if you look at it, it wouldn't be hard to simply convert from protobuf service definitions to WIT interfaces. Now, this creates an interesting situation where components would now have these heterogeneous interfaces as opposed to containers with their TCP ports that sort of appear more fungible to a platform, right? Because each component would have a unique interface based on the shape of the service that it implements. It allows us to bring pretty much all the boilerplate out of the individual workloads because now the platform has some visibility into how the service behaves. It can handle things like message serialization. It can handle, whether that's using protobuf, JSON, or some other format that can be expressed in this WIT language in a standardized way, or in any IDL, really, that can be converted. And, Google has had these protobuf extensions for a long time that they have in GCP that handle all sorts of things like auth and quota and, based on this well-established declarative syntax where you can do things like option, google.api.http, and you get JSON for free. You get HTTP 1.1 for free, even though this is ostensibly gRPC, right? Now, essentially, the platform can actually handle everything for us except this, the business logic. And all a component really has to do is export these individual, richly typed functions that actually serve the service that it's trying to implement. So for many common tasks it needs to accomplish also, like sending outgoing requests or logging or tracing or consuming feature flags, there can also be a standardized high-level interface that it imports from the host. And it provides those advanced features I was talking about cheaply, without all this duplication. Serverless platforms are sometimes called functions as a service, or FaaS. But that's hiding the fact that the simple-looking function you implement is actually just a tiny piece of the containerized unit of work that the platform actually ends up dealing with. And with a platform like this, the unit of work is actually just a function. See, existing FaaS platforms may be able to hide a bunch of their complexity from you, but they can't really hide the efficiency problems that it creates. Serverless is expensive. A serverless platform can easily cost like 10 times more than a regular VM handling the same traffic. But by eliminating essentially all of the boilerplate from individual components, we can increase the workload density on each node by a couple orders of magnitude, making serverless cheaper. So there's also something called WIT RPC, or WRPC, that is pretty recent. It basically just takes any WIT interface and makes it available over any L4 transport, like TCP or QUIC or Unix sockets. And this is pretty similar to the gRPC idea. In that, we're exposing individual elements of the service directly to clients and to the platform, but it has some distinct advantages. So, mainly, it supports all of WIT's features, including things like resources with instance methods that are a bit harder to model using gRPC. But it also has a couple disadvantages, in my opinion. You can't really support all of WIT, and also support things like JSON transcoding, right? Things that protobuf can do. So that basically means browser-based clients and one-off curl commands are kind of out of the question. So it also, I think, doesn't have as good of a story about API evolution as protobuf, because protobuf was designed to support, adding new fields, removing old fields from interfaces without breaking old clients. And WRPC supports these feature gates, so you can introduce and deprecate these whole functions and types with this since and deprecated syntax, but in my opinion, it's not as good of a fit for a distributed cloud as protobuf support for field level changes, but broadly speaking, both of these approaches aim to unlock this richer interface afforded by WebAssembly components, at least partially, and make it available over the network in some way. I don't know if anybody has some thoughts on this yet, or we can get to that at the end too. Great, well, I could stand up here and talk about interfaces all day, but how much can this actually save you? Now, that's unfortunately a pretty difficult question to answer because it really depends. And also, the two systems are different enough that the more you drill down, you realize you're just looking at apples and oranges here. But I came up with a bunch of numbers, and we're going to try to put some things in perspective here. So I compiled hello world examples. In C, Rust, Go, and Python, notice this is a log scale. No, this C bar is not white, but it's not visible despite the log scale. Now that Python component is pretty big because it ends up bundling in all of CPython, including the entire standard library, basically running an interpreter inside an interpreter. And that's really the only way to run true Python and WebAssembly today. There are a bunch of other projects doing, it's a rapidly evolving ecosystem, but just as a point of comparison there. So next I compiled basically the smallest bootstrap binary I could produce using AWS's Labs Rust runtime for Lambda. So, as most of you probably know, Lambda uses something called Firecracker instead of containers to virtualize their workloads. And running a Firecracker VM essentially involves booting up a KVM using a real Linux kernel and a real root file system and running a binary inside it that implements this Lambda runtime API. And this is the size I got for a size-optimized, statically linked, hello world bootstrap binary by itself. So next to it are sizes I got for a recent Linux kernel and an Alpine root file system. And basically, if you add up those pale orange bars, you get a vague idea of really the minimum runtime memory requirements of a hello world Lambda image. Now, sure, Firecracker can reuse the same kernel across VMs, but in order to achieve its strong isolation guarantees, it actually has to boot up a dedicated copy of that kernel in memory for each running VM. That's 40 megabytes of runtime baggage that WebAssembly just doesn't have to worry about thanks to its additive approach to isolation. And booting that kernel also totally dominates the cold start latency, which I measured on the next slide. But basically, the large binary there, that 3.47 megabytes, is a consequence of the poverty of the container's interface, where it has to implement this whole server for you, even though really you're just implementing a function. And the runtime cost of the kernel is the result of its subtractive approach to isolation. The root file system is sort of a bit of a consequence of both. You can't share it because of the strong isolation needs, and you need it because of you need to recreate this Linux environment. Of course, most people just use the normal base images for Lambda, which, I went ahead and measured those too. They're quite a bit larger than Alpine. Ends up being a couple hundred megabytes at a minimum. That provided base image is the one that just doesn't have any runtime. And finally, just as a point of comparison, I compiled a C++ gRPC server hello world example with reflection as a point of comparison. Now, gRPC reflection is another great example of boilerplate that the platform could handle for us thanks to this richer interface of the component model. See, the platform can tell just by looking at a component that it has a function called hello world that takes a string and returns a string or whatever it does, and it can report that via reflection or has an open API spec or whatever, and that doesn't have to be injected into an individual workload. It's just something the platform can infer. So again, these are hello world examples, so they're best understood as a measurement of boilerplate. If your workload involves a ton of business logic or is CPU bound, the advantages of WebAssembly are going to diminish. But if we're talking about microservices, like a megabyte is already a ton of business logic. I mean, just kind of sending out HTTP requests and maybe doing some basic data structure and algorithms. I don't think it's unrealistic to conclude that we're basically looking at 2 orders of magnitude smaller footprints on average using WebAssembly. So what does that mean? Well, it means each node can run a lot more pods, right? Probably on the order of 100 times more. And that could let you get away with a lot fewer nodes, lowering costs. It could also enable you to just spread each service across more backend nodes, improving load balancing flexibility and mitigating traffic bursts. And depending on your needs and your traffic patterns, you might want some combination of these 2 benefits because, 100 times greater density gives you plenty of leeway to allocate savings in multiple ways. Now, I'm not a Lambda expert. I know they have some tricks up their sleeve where, to reduce the likelihood of a true cold start. But when you do get a real cold start, booting up that Linux kernel generally takes on the order of 100 milliseconds. See, on Firecracker's website, they say you can initialize everything in as little as 125 milliseconds, and I benchmarked it a bunch of times on my laptop. I found that was accurate. But a true cold start in WebAssembly is basically a couple orders of magnitude faster. It's 2 milliseconds, quite consistently. And that's pretty negligible, right? But then you think about the trick Lambda can pull where they just keep a little extra capacity warm for you in case of a traffic burst, and you realize that trick would also be a lot easier to pull off with WebAssembly because of its vastly smaller footprint, right? I mean, keeping a WebAssembly component warm doesn't involve keeping a 40 megabyte Linux kernel in memory. So, either way you slice it, you're basically looking at a world where cold starts just like don't really exist for all intents and purposes. So hopefully, now these benefits seem less abstract. You have this richness of the interface that can eliminate basically all the boilerplate that would otherwise dominate our microservice images. And you have this bottom-up approach to isolation that lets us use system resources more intelligently and efficiently, including enabling things like transparent green threading and better management of the ephemerality problem. I think in 10 years' time, we're basically going to look back on when we used to use KVM to run our fast platforms and think, I can't believe we used to do that. But, WebAssembly provides, frankly, just kind of a more sensible approach for that use case. Of course, there will always be use cases where containers make more sense, like a long-running VPS or perhaps a resource-intensive LLM, but, one size will never fit all in the cloud. So finally, some of you might still be wondering, who am I and why am I rambling on about this? But basically, I've been working on this project that I'm getting ready to release, and it's about bringing a specific vision for WebAssembly pods to Kubernetes. And so I'm here to solicit your questions, your comments, your personal attacks. Please ask them now, or just email me if you're watching this recording at some other time. And yeah, I'd love to talk about it in even more depth than I already have.
What's up? Well, hey, you're more in this space than I am. I've just been loosely following it over the couple of years. So, knowing what you know, what's the deal with the internal memory situation, like the whole lack of read-only memory, the ability to write to null, and all that? Is there any movement in this direction, or is it kind of like, is there like a RFC or something that's kind of been waiting?
So the question is, what's the deal with internal memory? With, you said, memory safety, writing to null, and sorry, what was the other point?
Yeah, like writing to null, no lack of read-only memory, no ASLR,
Gotcha.
all that good stuff.
So it's a compiler target. So the tooling that you're using to actually compile to WebAssembly could enforce these invariants, right? Like if you're using a tool like Rust that has safe pointers, like you're not going to write to null, you could use language level features that enforce read-only memory, basically. I mean, when you look at the actual memory model of WebAssembly, it's based on, well, there's sort of two. One of them sort of being developed. It's the GC features of it. But right now we have good support for these linear memories, which are, they're always bounds checked. Accesses are always bounds checked. I think it's important to keep in mind that there's sort of two different types of modules. You have your core modules and your component modules. And I'm sort of arguing that component modules are this better fit because they actually offer more memory safety. They actually just don't let you share memory at all. So sort of the blast radius has been constrained to a module. If you're talking about untrusted code, basically, you would want language level features to enforce these safety invariants for you. And if you didn't do that, the blast radius is constrained for that module. I hope that answers your question.
Hey, good job. I agree with pretty much everything you say about the value of WebAssembly, except for the component model is worth investigating. I think a hot take is actually the component model is already dead, and the Biker Alliance is just trying to see it through to get their data into some standards. I'm curious what your thoughts are on the language support situation where the component model has been promising language interop and universal support for so many years. And can you truly tell me a language other than Rust that you feel like is pleasurable to work with the WebAssembly component model, either on the embedding side as a host or compiling to as a guest?
So yeah, it's a great question because yeah, support is not great. I've filed a couple bugs against TinyGo about this, trying to improve it. And this, this is an evolving standard. This is something that will take some time, and maybe it is disappointing how long it's taking. Because, at the end of the day, compilers were sort of designed to build essentially executables and not really these components that have like a pretty different way of running. So yeah, I mean, I don't dispute the fact that for most languages besides Rust, although I will say that C, C++ has pretty good support as well, but most languages besides those two, making components is pretty much a drag. So I don't dispute that. I'm working on improving it personally. I think maybe I'm a Bytecode Alliance Kool-Aid drinker, but I don't think it's dead.
My knowledge may be like a little bit out of date, but I remember a couple of years ago, we were trying to run WASM, and one of the challenges is like C, C++, Rust code, use synchronous I/O, and in a browser, for example, or in a serverless runtime, you don't do blocking I/O calls, and so then you have to emulate that, and there was quite a bit of overhead with that emulation, and so WASM actually ended up being quite a bit slower than even like a JavaScript snippet, which is surprising for someone like doing native kind of systems language for us. So I'm curious if that situation has improved, if it's been solved, like what's the...
Yeah, well, that's interesting because when you do I/O, you end up having to invoke functions that have been provided from the host, right? And it doesn't, like from the perspective of the module, it might look like it's a blocking synchronous call. But the host might actually implement it completely asynchronously, right? I mean, if you're using the sort of reference runtime, which is called WASM time, it's, there's a whole way to run everything asynchronously. So when you implement that I/O API, basically in Rust, you implement it asynchronously. And from the perspective of the app, you don't have to worry about that at all. There's no like function coloring problem, but it's not like the runtime is actually blocking on that I/O. It's just going to, add it to the, queue of things that it needs to do asynchronously.
My understanding was that when you do the block I/O call and to come back to it later, you have, like the compiler has to inject like checks of like, am I unblocking which function so that it can re-enter from the entry point of the module.
Huh.
At least back then that was...
Which runtime were you using? Was it WASM time?
No, it was like V8.
Okay, V8. Interesting. I'm not super familiar.
This is our last question.
Hi, thanks for the talk. I have a question regarding, so the sorts of components that you're describing were very much like a simple request comes in, we do some processing, and we return some output. But more realistically, we're always going to have something like a database that we want to talk to, or like some of these long persistent, or I mean typically persistent states. And I wonder how do you envision sort of integrating this where you spin up this WASM component quickly, but then you somehow need to give it access to all the external stuff that it will probably need.
Yeah. Okay. So this is asking about persistent state really, and there's two sort of ways you can do that. You could have totally external state, right, a database. But there's another way you could do it, which is having these, so WebAssembly already supports these things called shared memories, which means you can have a memory, a linear memory that is shared between multiple instances of a component, or maybe multiple different components really. So the way that could manifest is you compile your component, it declares a shared memory, and that shared memory could be like a cache or something, or maybe like, I don't know, some client credentials that, I don't know why you would need those to be persistent really, but say it's a cache, right? So that cache could then be populated by one instance, and then you spin up another instance, it has access to the same cache. That's something that exists already in the spec. It's really up to the platforms to make that easier to use, really.
I see, that makes sense. Thank you.
Cool. All right. Thank you.